Hey guys, my name is IBM and today I'm taking you into electricity and DC circuits. This is going to be, I think this is going to be lesson 2, and basically in lesson 2 we shall concentrate on, I think we shall concentrate on drift velocity, where we shall derive another equation of current. For example, my students always prefer to say current equals to never. So we are going to derive another expression for current. And basically, in lesson 2, we shall talk about EMF and potential difference, where we shall be able to explore the difference between EMF and potential difference. That will be the most important concepts. Those would be the most important concepts in this lesson. Just to remind you, in AS physics, you're supposed to study the following units: physical quantities, errors and uncertainties, treatment of uncertainties, kinematics, dynamics, force, density and pressure, work, energy and power, deformation of solids, waves and superposition, electricity and DC circuits, and particle physics. However, the units in red have already been covered, and therefore we are just remaining with the units in yellow. Currently, we are dealing with electricity and DC circuits. So let's move to lesson 2 of electricity and DC circuits. So don't forget, this is electricity and DC circuits. We are dealing with AS Physics 9702. Some of the concepts I've already explored in this unit are useful to GCSE students and students in other curricula such as AQA, I think even IB, but they are most likely going to these units or these tutorials are designed following the AS Physics curriculum of 9702. So this is lesson 2, and I want us to start or to delve very fast into what we're supposed to discuss today. So current and drift velocity of electrons. In lesson 1, we introduced electricity, where we reviewed the simple electric circuits, where we reviewed the electric symbols or the symbols used in electricity. And I told you that you should make yourselves comfortable with those symbols because you'll need them several times. We also talked about the meaning of electric current, where we defined electric current, and most importantly, we actually talked about we talked about charge as being quantized. So the three most important concepts we discussed were charge being quantized, the meaning of electric current, and the circuit symbols used in electricity. So we are going to concentrate on the fact that electrons are the most important charge carriers that are responsible for the flow of current, because we say the flow of current can be modeled as electrons moving from negative to positive, being equivalent to positive ions moving from positive to negative. That's why we say current flows from positive to negative and electrons flow from negative to positive. So, have you ever wondered why when you turn on light switch, the light comes on almost instantly? When you press the switch, normally the light comes on almost instantly. Of course, I know that many people think that electrons flow very rapidly from the socket to the light bulb. However, this is not the case. You press the switch and light comes on instantly. So, does it mean that the electrons are supposed to flow from the switch to the bulb? I don't think that is the case. All we know is that there is already current at all points in a circuit as soon as the circuit is completed. So when you press the switch, you're just completing the circuit. So as soon as the circuit is completed, there is already current. There's already current in the circuit as soon as you complete the circuit. So we don't have to wait for charge to travel around from the cell to maybe the bulb, or from the cell to the device which is going to use the electricity. And why is that possible, or why is that true? So this is because the charged electrons are already present throughout the metal before the cell is connected. There are already electrons in the wires, distributed all over the wires, all over the conductors. So because they are already there, when we close the switch or when we complete the circuit, we just set an electric field in the wires, which travels through the wire at near the speed of light. The charge carriers are already distributed all over the conductors. When we complete the circuit, we just set an electric field which moves through the wires, which move through the wire or which move through the wires at almost the speed of light. What does the electric field do? The electric field just sets electric charges in motion in one direction, thereby creating an instant current. So already electrons were already there between the switch and the bulb. They were already there. They were already there and free to move. But completing the circuit just sets them to move in one particular direction. That is from negative potential to positive potential in that sense or in that case. And therefore an electric current can be said to flow. So the mobile charged particles within a conductor move constantly in random directions like the particles of a gas. In order for there to be a net flow of charge, the particles must also move together in one direction with an average drift speed. So pressing the switch, you are completing the circuit. You are setting an electric field which is going to cause these electrons to instead now flow in one direction so that we have what we call a current, because a current must be flowing from a current will be flowing if the charge carriers are moving in one particular direction, not randomly in any direction. So now we know why when you turn on a light switch or a light bulb, when you turn on the switch of a bulb, the light comes on almost instantly. We already have charge carriers distributed all over the conductor. By completing the switch or by pressing the switch, we're just completing the circuit, creating a potential difference between 2 points so that an electric field is set up. The electric field aligns the charge carriers in one particular direction as they flow, and that means a current is supposed to flow. So in this unit, we are going to start, in this lesson, we are going to start by trying to derive an expression for current in terms of the number of charge carriers or the number of electrons, the cross-sectional area of a given wire or a conductor, the charge of the charge carrier, which may be the charge of an electron, and then the drift speed, because I've said in order for there to be a net flow of charge, the particles must also move together in one direction with an average drift rate or drift velocity, as we are going to see. So we need to derive an expression for relating current to the speed of the charge carriers in a conductor. So the net velocity of the charge carriers is going to be called the drift velocity. The net speed or the net velocity of the charge carriers, which in this case could be the electrons, is going to be called the drift velocity. So we are going to consider a section of a conductor, such as the one demonstrated here, whose cross-sectional area is, let's say, A in meters per second. If this conductor is cylindrical, then the cross-sectional area is circular, as shown by this part here. It is a circular cross-sectional area. So we're going to consider this section of a conductor. It can be part of a wire in which a current is flowing. In this animation, we are seeing that negative charge carriers are flowing from the left-hand side to the right-hand side. And we saw that according to Benjamin Franklin, current flows in the opposite direction to the negative electrons or to the charge carriers in this case. So let us assume that we have the number of free electrons per unit volume. Number of free electrons per unit volume be n. That means in a given volume or in 1 meter cubed of the conductor. Remember, the conductor is cylindrical. In the 1 meter cubed of the conductor, let us assume that the number of free electrons present is n. And we are going to assume that the charge on each conductor, on each electron or on each charge carrier, which travels a length L, represented by this animation and diagram, is E. So we are going to derive the expression current flowing through a conductor equals to N, that is the number of free electrons per unit volume, which we shall always call the charge density, and A, which is going to be the cross-sectional area of the conductor, times Q, which is going to be the charge of each charge carrier, times V. But because we normally consider an electron, Q is going to be equal to E, or the charge of the electron is equal to E. So my students will always tell me that is actually, my students always prefer to remember this as never, this equation as never, because it's easier for them to remember this. So we are going to derive an expression current is equal to never, where N is the number of free charge carriers per unit volume, which we shall call the charge density. E is the charge of each charge carrier, which is an electron. V is the average drift velocity of each of these electrons, and A is going to be the cross-sectional area. I want you to note from this animation that the current flows in the opposite direction to the charge carriers. That is very, very important to note. Okay, let's try to derive this, therefore. So, number one, we shall begin by finding, we already know that the cross-sectional area is A, and we have already defined N as being the number of free electrons per unit volume, and E being the charge of each charge carrier. So if N is the number of free electrons per unit volume, then we need to find the volume of this conductor. Of course, we know that the volume equals to cross-sectional area times another length, which in this case, the total volume of the conductor is going to be the cross-sectional area times the length L. So volume is going to be equal to A times L. Then remember we have n electrons per unit, n charge carriers per unit volume, and yet the total volume is A times L. That means total number of charge carriers or total number of electrons is going to be the volume times the number of electrons per unit volume. So the total number of electrons in this section that we have considered is going to be NaL. That is the volume times the number of electrons per unit volume. Then you also remember each charge carrier has a charge E, but the number of electrons in the whole section is NaL. If each charge carrier has a charge E, that means total charge is going to be E times the number of the charge carriers. Therefore, the amount of charge which leaves the left-hand side, for example, to the right-hand side is going to be N, that is the number of free NaL, which is going to be total number of electrons, times E, where E is the charge of each charge carrier or the charge of each electron. So what time does it take for a charge carrier to leave the left-hand side to the right-hand side? Because you remember, we know that current is the rate of flow of charge carriers. So at what rate are the charge carriers leaving or drifting from the left-hand side to the right-hand side? So we need to find the time it takes for a charged particle to leave, say, the left-hand side to the right-hand side. And the time is simply equal to the distance over the speed, assuming that the average drift speed is a constant. Therefore, the time taken for charge to travel the distance L is going to be T equals to L over V. Then by definition of current as the rate of flow of charge carriers, so current is going to be total charge over time, which means current is Q over T, and our Q is our total charge is NaLe. Then we divide this by time, which is L over V. And of course, when I do the algebra, this is over 1. When I do the cross multiplication here, I have that I is equal to NaLe times V over L, and this L cancels out. And therefore, I arrive at a simple expression that current equals to NaVe. So my students prefer to write it as simply current equals to never. Current equals to never, because this is easier for them to remember, where N is the number of free charge carriers per unit volume, E is the charge of the electron, V is the average drift speed or average drift velocity, and A is the cross-sectional area of the conductor. Sometimes the charge will not be an electron, and if the charge is not electrons, If the charge carriers are not electrons, then I will be quoted as NaVq, where Q in general is going to be the charge of the charge carrier in that case. So note very carefully that different materials or different wires may have different values of N. For example, semiconductor will not have the same value of N as a pure conductor, because N is the number of free electrons per unit volume, or the charge density. We don't expect a semiconductor to have the same number of electrons per unit volume as a metal. So different materials will have different values of N, and conductors such as metals have the most charge carriers. So that's why they are actually good conductors. Semiconductors have fewer charge carriers than metals. So the value of N for semiconductors is very small. And that's why semiconductors are not as good in conduction as metals. Because for metals, they have a large number of free electrons per unit volume, and therefore it makes them to be better conductors. So you should be able to derive such an expression from simpler explanations. You should be able to derive such an expression. If we know the length of the conductor and the cross-sectional area, we should be able to obtain the volume. If we know that N is the number of free electrons per unit volume, we should be able to obtain total number of electrons. If we know the total number of electrons and we know the charge of each electron, then we should be able to find total charge which passes through the conductor in a given time. And the time for a charge carrier to leave one end to another end is the distance divided by the speed. So from definition of current as the rate of flow of charge carriers, or total charge divided by time, we should be able to arrive at an expression such as I equals NaVq. And we shall be using this expression many times in calculations. In summary, so we have arrived at a simpler expression that I equals to NaVq, where I is going to be the current in the conductor. It should be measured in amperes. N is going to be the number of free electrons per unit volume. Now, when you say number of electrons, that doesn't make sense. It is the number of electrons per unit volume, or it is called the charge density. Because number of electrons, number of charge carriers divided by volume is equivalent to the charge density. And A, we said A is the cross-sectional area. It must be measured in meters squared. And V is the average drift velocity or average drift speed in meters per second. And Q is the magnitude of charge on each charge carrier. It should be in columns. So of course the charge carrier could be having a negative sign or a positive sign in columns, but Q is the magnitude. Okay, so let's try to use this expression before we go any further. This is one of the expressions you never mentioned in GCSE. So here I have a self-check. This is supposed to be a classroom activity for my students, but I'll try to give a hint on each of these questions. A metal wire has 17 times 10 to the power of 28 free electrons. The wire has a current of 4.0 amperes and a cross-sectional area of 1.2 meters per second squared. Calculate the average drift speed of the electrons. Charge of the electron is given as 1.6 times 10 to the power of minus 19. So if we assume that 17 times 10 to the power of 28 free electrons is the number of free electrons per unit volume, so we shall find the average drift speed. Remember, we have said I equals to never, or this can be Q. So average drift speed V is going to be equal to I divided by current divided by NQ times A. So I'll just substitute. This will be 4.0 divided by, why isn't it green color it's not very good. So we shall say n is 17 times 10 to the power of 28 times, remember I'm dividing, q is 1.6 times 10 to the power of minus 19 times cross-sectional area. I have to change the cross-sectional area into meters squared. So 1 millimeter is 1,000. 1 meter is 1,000 millimeters. So it means 1 meter squared is going to be 1 million millimeters. So this will be 1.2 times 10 to the power of minus 6 to change it to meters squared. So I'm going to check my calculator. I'll start with the denominator because it's very big. So in the denominator, I have 17 exponent 28 times 1.6 exponent minus 19 times 1.2 exponent minus 6. So I will say 4 divided by the denominator, which gives me 1.225 times 10 to the power of minus 4. So I think this is correct. You can also verify. The average drift speed in a metal wire is 1.3 times 10 to the power of minus 4 meters per second when the current is 1.6. The diameter of the wire is 1 millimeter. Calculate the number of free electrons per unit volume in the wire. So we want to find N. Number one, I want you to note that cross-sectional area is equal to pi, because it is circular, area is equal to pi r squared, which is the same as pi d squared divided by 4. That is the area. And we know that current equals to never. So I want to find N. So making N the subject, remember the area is pi d squared over 4 because they have given us the diameter. So N is going to be equal to I divided by EVA. So it means N is going to be the current, which is 1.6 divided by the charge of the electron is 1.6 times 10 to the power of minus 19 times drift velocity is 1.3 times 10 to the power of minus 4 times the area, which area is pi d squared. So it is going to be pi. Diameter is 1 times 10 to the power of minus 3, and this should be squared divided by 4. So the whole of this is the denominator. So I'll start by simplifying the denominator in my calculator. Shift pi times 1.3 exponent, 1 exponent minus 3, but this should be squared, divided by 4 times 1.3 exponent minus 4 times 1.6 exponent minus 19. Then I'll say 1.6 divided by the answer. So this is 9.79 times 10 to the power of 28. So this is correct. You can also verify with your calculator. Copper wires can conduct about 10 amperes per millimeter squared before overheating, and there are approximately 10 to the power of 20 free electrons per millimeter cubed in copper. Calculate the number of electrons per second required to carry a current of 10 amperes. So we want to calculate or to determine the number of electrons per second required to carry 10 amperes. So I'm very certain many of us will confuse the number of free electrons per second with the number of electrons per unit volume, or number of free electrons per unit volume. So when I talk about just number of electrons per second or per unit time, I can use capital N for that. But for small n is going to be the number of free electrons per unit volume. In other words, if I divide n by volume, I get small n. Okay, so I'll capture the number of electrons per second. So number of electrons, remember charge equals the number of electrons times the charge of each electron. And this is equal to I times T. But remember T is 1 second and the current is 10. So it means the number of electrons we are talking about here is going to be the current, which is 10, times the time, which is 1 second, divided by the charge of each electron, which is 1.6 times 10 to the power of minus 19. And I think this answer is correct. You can also verify with your calculator, but I think this should be correct. 6.25 times 10 to the power of 19. Then the length of a wire with a cross section 1 millimeter squared containing this number of electrons. So remember we said the number of electrons n is equal to 6.25 times 10 to the power of 19. But if I want to find small n is the number of electrons divided by the volume. The number of free electrons divided by volume is number of free electrons per unit volume, and this has been given as 10 to the power of 20. So when I divide both sides by V, both sides, and remember volume also, volume is equal to cross-sectional area times L, and the area has been given. So I'll not change the units because I know the answers are in millimeters. So I'll have that N over V is equal to small n, which is 10 to the power of 20, but is per millimeter. So I'll say this is 10 to the power of 20 per millimeter cubed. Should be equal to 6.25 times 10 to the power of 19 divided by the volume, which is cross-sectional area, times L, which L we want to find. So volume is cross-sectional area times L. The area is given as 1 millimeter squared, then times L. So I just make L the subject. So I'm making L the subject by dividing. So millimeters squared cancels with that. So the answer is in millimeters. So I have 6.25 exponent 19 divided by exponent 20. So this gives me 0.625 millimeters, which makes this correct. Then the average drift speed. So I know that I is equal to never. I don't have enough space, so I'm trying to economize this space. So I equals to never, and I want to find V. So I'm just going to substitute without changing the units, but being careful with the units, I know that the units are going to cancel out. So the current is 10 amperes is equal to N. N is 10 to the power of 20 per millimeter cubed. The reason as to why I'm putting the units is to be sure that I arrive at the same the units of millimeters times E. E is 1.6 times 10 to the power of minus 19 coulombs. But remember, coulombs is the same as ampere seconds. Those are the units. Then times the average drift speed. Then the area is 1 millimeter squared. So millimeter squared is cancelling with the cubed. Amperes is cancelling the amperes of current. So the answer is going to be, when I take millimeters on the left-hand side, it becomes millimeters. Then when I take seconds, it becomes millimeters per second. So when I make V the subject, my answer is going to be millimeters per second. Let me just press my calculator. I'm making V the subject. So V is going to be equal to 10 millimeters divided by 10 power 20 times 1.6 times 10 to the power of minus 19 seconds because amperes has cancelled out. So my answer should be in millimeters per second, and when you press your calculator, that is correct. Then, if the same wire carried a current of 10 milliamperes, what would the drift velocity be, and how long would it take a typical electron to drift through 1 millimeter? Since I don't have enough space, I'll change the color. Of course, for you are doing this in a book, so there's nothing to worry about. So this time the current is 10 milliamperes, so I'm just substituting, I'm just making the same, you just substitute where there is 10 amperes, you put there 10 milliamperes. So we'll say 10 milliamperes, of course, millis times 10 to the power of minus 3 amperes equals to the 10 to the power of 20, that is per millimeter cubed. 1.6 times 10 to the power of minus 19 ampere seconds times V times 1 millimeter squared. So again, this cancels out. And when you press the calculator, I hope you get this answer here. It should be correct. Then to find the time, of course, time is going to be equal to the distance divided by the drift speed. The distance is 1 millimeter divided by the drift speed, which is 6.25 times 10 to the power of minus 4. And I think this should give you 1,600. Let me check it again. 1 divided by 6.25 exponent minus 4. So it is 1,600. So you can do your working systematical and check if the answers are correct. Okay, so we have been using the equation I equals to never, and now it should become part of U. For more questions, visit the Solve the Past Paper questions. Let's talk about measuring current or measuring current measuring instruments. Of course, we know from GCSE that current can be measured using the ammeter. We are used to the ammeter, so I will not waste time on what we already know. So electric current is measured using a sensitive instrument called the ammeter, or it can be a multimeter, but when you say multimeter, it should be on the ohms setting or the ampere set. So not the ohms setting, ampere setting. So if it is an ammeter, we are used to the ammeter, but if it is a multimeter, you must change it to the ampere setting if you want to use it to measure current. So it should be to the ampere setting. And the ammeter is used for large current, but for smaller currents, normally we use what we call a milliammeter. Milli meaning 10 to the power of minus 3. Or we can use a microammeter, micro meaning 10 to the power of minus 6. So these ones could be, they are still ammeters anyways, but they can measure smaller currents. Sometimes galvanometers are also used for detecting electric current, but this is less often. So you can't say I use a galvanometer to measure current. This is less often. Something has to be done to a galvanometer for it to be able to measure current. But most importantly, it is the ammeter or the multimeter on the ampere setting. So an ammeter is always connected in a circuit such that its positive terminal is connected to the positive terminal of the cell. We join the positive terminal of the ammeter to the positive terminal of the cell if we are measuring current through the ammeter. This is because the current flows directly through it. That is, it is connected in series. So whenever you're joining an ammeter, if this is the positive terminal you have chosen and this is the negative terminal of the ammeter, then you must join the positive terminal to the positive terminal of the cell, and the negative terminal should be to the negative terminal of the cell. That's how we connect an ammeter. Positive terminal is connected to positive terminal of the cell. Positive terminal of the ammeter must be connected to the positive terminal of the cell. That is very important to note. And the current should flow through it. That is, the ammeter is connected in series. So that's how we use an ammeter. And if I'm to demonstrate this, ammeters are always connected in series. They should be connected in series because they measure current which goes through them. So that's why we connect them in series, because they should give the current which goes through them as through a circuit. So this connection ensures that the entire current that passes through a device also goes through the ammeter. So we can't connect the ammeter across a device, because if we connect it across a device, some current may branch into the ammeter and another amount of current continues in another branch of the ammeter. However, we connected the ammeter in a series with a circuit, so that we measure the current which goes through the ammeter as being the current which goes through the whole circuit. So that's why the ammeter should be connected in series. Remember, I said the positive end of the ammeter should be joined to the positive terminal of the battery, and the negative end of the ammeter should be joined to the negative terminal of the battery. That is the correct way of connecting an ammeter. So for this reason, an ammeter should have as low resistance as possible, because it's measuring current through the circuit and the same current should go through the ammeter. Then the ammeter should have as low resistance as possible. It should have as low resistance as possible, because inserting an ammeter with a high resistance could significantly reduce the current flowing through the circuit. Because the ammeter is going to measure the current which goes through the circuit, and that current should go through the ammeter. The ammeter should have as low resistance as possible, so that as much as possible, so that a very small current can be lost within the ammeter, or a very small an insignificant amount of current can be reduced from flowing through the ammeter. What does this imply? To ensure that the ammeter is effective, or as effective as possible, and its resistance is as low as possible, we would simply say that an ideal resistance of an ammeter should be zero. I'm using the word ideal, which means it is practically not possible to have an ammeter whose resistance is zero. However, it would be the best ammeter if its resistance would be zero, but in a practice, we can't have such an ammeter, simply because the ammeters are made up of electronic components which have some resistance, even though we try as much as possible to ensure that the resistance of the electronic components used in the ammeters are extremely small. The resistance of the wires are extremely small, but still their resistance is not zero. However, an ideal resistance of an ammeter would be zero, or is supposed to be zero, because the ammeter is designed to measure the current through. Therefore, it shouldn't reduce much, it shouldn't prevent current flow through it, because it is connected in series. Like I said, we can also use a galvanometer to measure current. However, a galvanometer cannot be considered as a standard component for measuring current, because something has to be done to it. A galvanometer may be converted into an ammeter, and this can be done by connection of a suitable resistor in parallel with the ammeter. Because the galvanometer has some good resistance, we are going to choose another resistor to connect it in parallel. From your GCSE concepts, you notice that when resistors are joined in parallel, the total effective resistance becomes small. The reason as to why we are looking for a suitable resistor to connect it in parallel with the galvanometer, we are trying to make the resistance of the galvanometer to be as small as possible, because we don't want to prevent current flowing through the circuit. We want it to allow as much current as possible flowing through the circuit if the resistance is small. And such a resistor we are going to choose, we are going to call it a shunt. So the resistor we are going to use to make sure that the resistance of the galvanometer is reduced, so that the galvanometer can measure as much current as possible going through it, is going to be called a shunt. So the net effect is going to be that we have the galvanometer and another resistor. And remember, for resistors in parallel, total effective resistance is smaller than the resistance of the smallest resistor. total resistance is smaller than the smallest resistance in the combination or in the circuit. Okay, so by doing that, we are converting the galvanometer into an ammeter. So the shunt makes the resultant ammeter a very low resistance device. This is desirable because the insertion of the ammeter into a circuit must not change the current it is supposed to measure. So if we now connect this to a circuit whose current we want to measure in the presence of a shunt, the total effective resistance of this part here is going to be very, very small. So we say we have converted the the galvanometer into an ammeter. So to convert a galvanometer into an ammeter, we use what we call a shunt, a suitable resistor which makes the effective resistance or the total, which reduces the total resistance of the coil of the galvanometer, or which makes total resistance to be very small so that the galvanometer can register as much current as possible. So an ammeter would be used to measure, an AC ammeter by the way, would be used to measure alternating current. That is current that reverses direction. So for alternating current, we could use an AC ammeter. It is still an ammeter, but it's an AC ammeter. For DC current, we normally use the ordinary ammeter, but if it is alternating current which keeps changing direction, which we shall see in paper 4, current which changes direction, we can use what we call an AC ammeter. Of course, we may not use a galvanometer in this case, but of course, we have mentioned we use a shunt or a suitable resistor to make sure that the resistance of the galvanometer is very small so that it can now be used for other purposes such as measuring current. That suitable resistor is called a shunt. We shall see the importance of the galvanometer under the null method in potential dividers. So that is how we measure current. We said we use an ammeter, or if the current is very small, we might use a milliammeter, or we can use a microammeter, or we could use a multimeter on the ampere setting. If the current keeps changing direction, we now use what we call an alternating current ammeter. By the way, we also have what we call a calibrated cathode ray oscilloscope. The calibrated cathode ray oscilloscope. I will talk about it later on. So let's talk about the PD and EMF. So having measured current, we should talk about the PD and EMF. So what do we mean by PD and EMF, and what is the difference between PD and EMF? You might also have talked about this in GCSE. So we know that a cell makes one end of a given circuit positive and it makes the other end to be negative. So when you connect a cell and complete the circuit, one end of the circuit is positive, one end of the circuit is negative, or one end of the cell makes one end of the circuit to be positive and makes the other end to be negative. So we say the cell has set up what we call a potential difference. We would say an electric field has been set up. So the PED, as we mentioned in IGCSE, it is measured in a unit called the volts. So when I talk about PD, is potential difference. Writing PD is allowed at this level, or sometimes we can call the voltage. So you should never talk about PD or voltage through. You should never talk about PD or voltage through. We have been talking about current through the circuit, current through the ammeter, current through the bulb, current through the lamp, current through the heater. I can't talk about PD through the heater. That doesn't make any sense. Because when a cell is connected across a circuit, it makes one end positive, another end negative. And the difference in potential is what we call potential difference. So it's like potential difference is between 2 points. So we can't say potential difference through 2 points. No, potential difference between 2 points. There's a difference in potential between 2 points. So you should never talk about PD or voltage through a device because it is in fact difference. This is a difference in potential across the ends of the device. So the PD provides energy. The PD provides energy to charge through the device that the current flows. The PD provides energy to move charge through the device that current flows. So uh, by creating a potential difference between 2 points, energy is provided which is going to accelerate a charge through the device. So later on we may talk about it as accelerating PD. Therefore, therefore, we shall say that the potential difference between any 2 points in a circuit is a measure of electrical energy transferred into other forms like light, heat, sound by each column of charge as it passes from one point to another. Electrical energy transferred most importantly heat. Electrical energy transferred into other forms like light, heat, sound by each column of charge as it passes from one point to the other point, or as it passes through a given component, or as it passes through a given device. For examination purposes, we can just define PD as the energy transferred in the circuit per unit charge. The energy transferred in the circuit per unit charge, that is PD. Energy transferred in the circuit per unit charge, that is PD. Or you can define PD as the work done when one column of charge moves from one point to another in a circuit. The work done when one column of charge moves from one point to another in a circuit, that is potential difference. Energy transferred in the circuit per unit charge. It must be in the circuit because there is a relationship between EMF and PD. They have the same formula and the same units. And in both cases, energy is involved. So we must be very careful to define PD as the energy transferred in the circuit per unit charge. Okay, so we are able now to define PD in terms of energy as the energy transferred in a circuit per unit charge, or the work done when one column of charge moves from one point to another, or the work done to move one column of a charge around a closed circuit, that is PD. So whenever current flows from one point to another, it does so because the electrical potential at these 2 points are different. Of course, if 2 points have the same potential, or 2 points had the same potential, both of them, let's say they are negative, and they are also both having the same magnitude of the negative sign, it means there is no difference in potential. So if there is no difference in potential between 2 points, if the points are at the same potential, that means there is no difference in potential between 2 points, then no current can flow between them. So what does that mean? Electrons flow from a lower. Electrons are supposed to flow from a lower to a higher potential. And if 2 points are the same potential, then there will be no electron flow because we expect the electrons to flow from a lower to a higher potential. And if the 2 points are the same potential, then electrons cannot flow. And if there are no electrons flowing, then we don't expect a current to be flowing. So in a nutshell, I'm saying if there's no difference in potential, then we don't expect a current to flow because a current only flows when there's a difference in potential. So the SI units of potential difference, we have already mentioned that this is the volt that we know from GCSE. And we can define the volt from the definition of potential difference. Remember, potential difference was the energy transferred in a circuit per unit charge. And energy, we shall use W for energy, which is going to be measured in joules. And the charge, we shall measure it in coulombs. We shall be able to define the SI unit of the volt from this definition of PD. However, before we define the units, other units of potential difference, if the voltage is very small, we can use millivolts. If the voltage is very big, we may talk about kilovolts. We know what milli stands for. Milli stands for 10 to the power of minus 3. and kilo stands for 10 to the power of 3. That is potential difference. So from the definition of potential difference as energy transferred, that is from electrical to other forms such as heat, light, sound, etc. point charge. So, and it is also the work done to move a column of charge from one point to another. Work done or energy transferred is W. We shall use W for energy transferred and Q for charge. And from this, we shall be able to define other units. We shall be able to define the unit, the volt. Remember, we defined the unit coulomb as ampere seconds. Now we are going to define the unit volt. Since work done is sometimes measured in joules and charge is measured in coulombs, then it doesn't do any harm for us to define a volt as 1 joule per coulomb. So we shall define the volt as 1 joule per coulomb. So the energy transferred or work done, W, is PD times charge. Sometimes we shall be using the expression work done as charge times V, or work done as QV, or work done as being equal to EV. Later on, as we advance, we shall be using energy as EQ. EV, not EQ. Or kinetic energy becoming the work done. If, for example, an electron is accelerated, the work done is going to be called the kinetic energy, which we shall later on see that it becomes E times V, where E is the charge and V is the accelerating speed. So it doesn't cause any harm for us to say that the work done is equal to charge times potential difference V. So, and from that, we therefore conclude that if work done is measured in joules and charge is measured in coulombs, therefore we should be able to define a volt as 1 joule per coulomb. So a volt is defined as the potential difference between 2 points when 1 joule of work is done in moving 1 coulomb of charge between the points. For examination purposes, we can just define a volt as 1 joule per coulomb. Many times we define units in terms of other units from which they have been derived. And sometimes we can define quantities in terms of other quantities from which they are being derived. So we can define a volt as 1 joule per coulomb. So let's try to understand briefly what we mean by potential difference. What have I been talking about? Let's consider a circuit such as this. When we connect the circuit or when we close the switch in this circuit, we make one end of the circuit positive or at a high potential, another side to be negative, maybe at a lower potential. But let's start by considering one side to be at 1.5 volts and maybe another side to be at 0.0 volts. So as electrons move from one point to another, they carry charge. Oh, the electrons are the charge carriers. So this charge, when this charge goes through the conductor, we expect that the energy is lost to the conductor or the device. So if this reaches at 1 point, so this point is say going to be 1.5, let's say the other side is at 0. So there's a potential difference between the two ends of the conductor, which means or which will constitute a current. So it will make electrons to be drifted through the conductor. If this conductor is now the bulb, if this device is the bulb, then the bulb is expected to light because current is now flowing through the bulb. And it means there's a potential difference between the two, which we are going to call the PD across the conductor. And this is what we mean by potential difference. So if there's a difference in potential, all the 1.5 volts are maybe lost to the bulb, it means the other side should be at 0 potential. And that's what we call potential difference. So the charge carrier continues and it goes back. It is expected to go back to the battery to get another 1.5, for example, as the process continues, lighting the bulb. Example. Electrons in a television tube are accelerated by a PD of 40 kilovolts. Between filament and the screen, the charge of the electron is negative 1.6 times 10 to the power of minus 19 coulombs. Calculate the gain in kinetic energy of each electron. So if the electrons gain their kinetic energy from the PD or the accelerating PD, then it means the work done to move these electrons is the gain in kinetic energy, which is going to be obtained from the same expression that we already know. So from potential difference equals to work done per unit charge, it means the work done is going to be the charge times the accelerating PD. So the electrical energy transferred to the electrons becomes the kinetic energy of the electrons, or the work done becomes the gain in kinetic energy, which therefore implies that the work done has become the gain in kinetic energy, but the work done is the charge times the accelerating PD. Therefore, it will be the accelerating PD times the charge, which becomes, I think, 6.4 times 10 to the power of minus 15 joules. I will check this. So we say that the work done by the accelerating PD has become the kinetic energy. If I want to find the speed of this electron, therefore, I could say the kinetic energy, Ke, can also be a half mv squared, which is the charge times the accelerating PD. So I may find the drift speed, which would be the charge times the accelerating PD divided by m. There is a 2 here, and I find the square root, making V the subject, where m would be the mass of the charge carrier, which is 9.11 times 10 to the power of minus 31. V is the accelerating PD, Q is the charge of the charge carrier, which is the charge of the electron. So I would get the drift speed, or the speed with which the electrons move through the circuit. Example number 2, an electron in a particle accelerator is said to have 1 mega electron volts of energy when it has been accelerated through a potential difference of 1 million volts. Of course, mega means 1 million. Calculate the energy in joules gained by the electron. Of course, the unit electron volt may not be very common at this level, but I will still talk about it. So from energy equals to the gain in kinetic energy, the work done is equal to the gain in kinetic energy, but the work done is the charge times the accelerating PD, but the charge is an electron, so the charge is going to be E, then times the accelerating PD. When we talk about 1 electron volt, it is 1 electron times 1 volt. So 1 electron has a charge is 1.6 times 10 to the power of minus 19 coulombs, then times 1 volt. A coulomb times a volt will give us the joules, because remember we saw that V was equal to the work done divided by the charge. This was in joules, this was in coulombs, and this was in volts. So it means a coulomb times a volt gives us the joule. So when I talk about 1 electron volt, 1 electron volt is the same as 1.6 times 10 to the power of minus 19 joules. So it is the charge of 1 electron times 1 volt. Therefore, 1 electron volt is the same as 1.6 times 10 to the power of minus 19 joules. We shall many times talk about this unit, especially in A level, not necessarily in AS physics, but mostly or most especially in A level paper 4. That's when we shall mostly talk about the electron volt. Okay, so if we substitute, of course, mega means 1 million, that is 10 to the power of 6. So I just substituted in this equation here. Work done is equal to charge times accelerating PD, where the PD is 1 megavolts, which is 1 million volts, times the charge, which gives us 1.6 times 10 to the power of minus 19 joules. So in other words, 1 mega electron volt is the same as 1.6 times 10 to the power of minus 13 joules, as we shall see in paper 4. One more example, maybe a torch bulb is rated 2.2 volts, 0.25 amperes. Calculate the charge passing through the bulb in 2 minutes. Of course, here this is very simple. Charge is equal to IT. We have charge, we have the current times time should be 2 times 60. Change it to seconds. The energy transferred by the passage of each coulomb of charge. So remember we said PD is equal to the energy per unit charge. So it means the energy should be equal to the charge times the accelerating PD. So in our solution, we have that charge is equal to IT, which I think 30 coulombs is correct. And we have that the energy transferred or the work done is going to be charge times accelerating PD, which gives us 66 joules. So that is all I could say about PD, because you saw this in IGCSE. So the only thing you may not have used in IGCSE is PD being equal to work done per unit charge, or PD being equal to energy per unit charge in calculation. Let's also briefly talk about EMF. So what is the difference between EMF and PD? We saw that when a battery is connected in a circuit, it makes one end of the circuit positive, another end of the circuit negative. In the absence of the battery, we don't have a difference in potential, no current flows. So it means that the battery is the origin of a difference in potential. So when charge passes through a power supply, such as a battery, it gains electrical energy from the battery. If the battery is made out of chemicals, the charge is getting its electrical energy from the chemical energy stored in the battery. In other words, the chemical energy stored in the battery is being converted into electrical energy to give this energy to any charge which passes through the battery. So the power supply, therefore, is said to be an electromotive force, or the EMF. Some people write this as electromagnetic force. Just write EMF if you're not sure. So the power supply is the EMF, or is said to be the electromotive force. The electromotive force is actually the total energy available in the circuit. We don't expect the PD to be greater than the EMF. It is the maximum we can have in the circuit, because if the power supply is the cell, we don't expect the total energy within the circuit to be more than what has been supplied. So the EMF can be thought of as the maximum energy a cell can produce. The maximum energy that a cell can produce, that is the EMF. The maximum energy that a cell can produce. And like I said, we don't expect a cell to produce, we don't expect the EMF or the PD to be greater than what can be supplied by the cell. That would be violating the law of conservation of energy, which we mentioned in the unit called work, energy, and power. Therefore, we can define EMF in several simpler ways. EMF is the electrical energy gained by each coulomb of charge that passes through the power supply. This is the easiest definition of EMF. When a coulomb of charge goes through the battery, it gains energy. When the coulomb of charge passes through a bulb, for example, it gives out the energy. So in the battery, the chemical energy becomes electrical energy. When it reaches a device or a bulb, the electrical energy it has gained becomes other forms such as heat or light. So EMF is the electrical energy gained by each coulomb of charge that passes through the power supply. Electrical energy gained by each coulomb of charge that passes through the power supply. The energy gained comes from the chemical energy of the battery if it is made out of chemicals. So the EMF is the energy transferred by a source in driving a unit charge around a complete circuit. So the EMF is transferred by the source. It is by the source. Yet the PD, it is by the circuit itself. So the energy transferred by the source in driving a unit charge around a complete circuit is what we call the EMF. The electrical energy gained by a column of charge or gained by a charge as it passes through a power supply, that is the EMF. Or we can think about it as the energy transferred by the source in driving a unit charge around a complete circuit, that is the EMF. Of course, in both cases, it is energy per unit charge. So still, even in EMF, we are talking about energy per unit charge, but these types of energies are different. So it's like both of them are going to be measured in the same units as the volt, I mean as the PD. So the EMF and the PD are measured in the same unit, which is the volts or joules per coulomb. So then what is the difference between EMF and PD? Let's explore the difference between EMF and PD. So before we explore the difference between EMF and PD, I just want to summarize the difference. I mean, this in formula, EMF will be the energy converted from other forms to electrical. In most cases, it is energy converted from the power supply to other forms, such as, I mean, from the power supply to electrical. In most cases, if the power supply is a battery, this energy is converted from chemicals. So when the charge passes through a resistor, its electrical energy is converted to heat energy in the resistor. This is said to have a PD across it. And the PD is the electrical energy converted for each coulomb of charge that passes through it. So that is the PD. But for the EMF, it is the energy converted from other forms to electrical, which electrical now becomes other forms such as heat when the charge passes through an electrical device or when passes through a resistor or anything which uses energy. So I want you to mark clearly the difference between PD and EMF. PD is the electrical energy converted to other forms per unit charge. Energy transferred in the circuit per unit charge, that is PD. Yet EMF is the energy converted from other forms, especially chemical, to electrical per unit charge. That is the major difference. Energy transferred by this power supply to the circuit, or energy transferred to the charge or to a unit charge by the power supply, that is the EMF. Yet PD is the energy transferred by the charge to the circuit as it moves around the circuit, that is the PD. So energy converted from electrical to thermal per unit charge, that is PD, and energy converted from chemical to electrical per unit charge, that is the EMF. So that is the difference. For example, if I say that 1.5 volt cell gives 1.5 joules to each coulomb of charge which passes through it. If the cell has 1.5 volts, we expect that it gives 1.5 joules of energy to every one coulomb of charge which passes through the cell. That is what we call the EMF. So let's understand the difference between the two therefore. Let's consider Mr. Coulomb's analysis to understand the difference between EMF and PD. So Mr. Coulomb comes to the power supply with his empty sac. Mr. Coulomb comes to the power supply with his empty sac. So we are understanding what we mean by the EMF. In the power supply, we expect that that's where energy originates from. It is the source of energy for this matter. So while Mr. Coulomb is at the power supply, his sac must be filled. So the energy in the power supply has been converted to electrical to give Mr. Coulomb to continue on his journey. So Mr. Coulomb now has enough energy to move around the circuit. When Mr. Coulomb reaches the battery, Mr. Column gives some of his energy, the bulb. Mr. Column gives some of his energy to the bulb, which makes the bulb to light and also to give some heat around the bulb. So here we have the EMF because the energy has been converted or energy has been transferred by the power supply to the charge. And here the energy has been transferred from the charge to the bulb. So here we have what we call the PD. On the device we have the PD. On the power supply we have the EMF. So we should mark that difference very well. The power supply we have the EMF, the device we have the PD. So EMF is energy transferred by the battery to the electrons or the charges. Then PD is the energy transferred by the electrons to the components of the circuit. So both of them are involving energy transfer, but EMF is transferred by the power supply to the charges. Yet PD is transferred by the charges to the components in the circuit. Where the energy is supplied, that is the battery, we have the EMF, and where the energy is used up, the lamps, the resistors, the heaters that we shall be talking about, we have the PD. So now we know the difference between PD and EMF. For PD, energy is transferred by the charges to the components in the circuit. Yet for the EMF, energy is transferred by the power supply to the charges or to the charge carriers to that effect. Okay, so to understand this in more details, we are still exploring the difference between EMF and PD. So I just want people to understand that the EMF is at where we have the power supply. So in this simple circuit that I've indicated here, I have a battery connected to a bulb. And when a current is being delivered, when a current is being supplied, the voltage is going to be lower than the EMF. Of course, the voltage will be measured across the bulb. When there is a current being supplied, the voltage is expected to be lower than the EMF because some energy is going to be wasted inside the cell. If there is no current flowing, the voltage and the EMF are going to be the same. If there's a switch here and the switch is opened and there's no current being supplied, the voltage and the EMF are the same. But if there's a current being supplied, the voltage is expected to be less than the EMF, or the PD is expected to be less than the EMF. It can't be more than the EMF because this would mean that the law of conservation of energy is violated. So a cell produces its maximum PD when not in a circuit and not supplying current. So if the cell is not supplying current, then it is producing its maximum PD, which is going to be the same as the EMF. But the moment it starts giving out a current, some of the energy is wasted within the power supply itself. So the cell gives out less PD. So we are saying a cell produces its maximum PD when not in a circuit and not supplying a current. That is a very important question you should always consider. Whenever the cell is not supplying a current, the PD across the cell is the same as the EMF and it is maximum. When it is supplying the current, the PD across the cell is the same as the voltage. It is actually terminal PD, which is going to be less than the EMF of the cell. That is very important. So the EMF is the energy supplied by the source in driving a charge around a complete circuit. So I want people to understand, or the takeaway here is that EMF is the energy supplied by the source, the power supply, to drive a charge around the circuit. The energy transferred to the charge carrier, to every charge carrier, is the EMF. Yet the energy transferred by the charge carrier to the components in the circuit is the PD. Here's a simple example to understand the difference. 4 lamps are connected in series to a battery. State the energy transformations that occur in the battery. Of course, in the battery we have chemicals. So we know that the charge gains its electrical energy from the chemicals. So it is chemical energy to electrical energy. Then in the lamps, the charge gives out its energy to the lamps. The energy the charge the energy which the charge already has is electrical. So the electrical energy of the charge becomes the thermal energy in the lamp and maybe light of the lamp. Each lamp in A has a resistance R and EMF E. The current in the circuit is I. State the rate of energy transformation, that is power, in the battery. Of course, we are going to see this later on. Power is equal to energy divided by T, which was work done over T. We shall see this later on. But from your GCSE, you also remember that power is equal to I times V. If we consider the battery, V is equal to the EMF. That's why power in the battery, or the rate of energy transfer in the battery, is the current times the EMF. But in the lamp, the power dissipated is I times V, where V is the PD across the lamp. Remember I said if the power supply is supplying a current, the PD is less than the EMF. So if we consider a lamp, V is going to be the PD, which could also be I squared times R, that is from V equals to IR, which we shall see, or which we shall call Ohm's law later on, but you saw this in GCSE. So that is the difference between EMF and PD. So how do we measure EMF and PD? You also saw this in GCSE. It is not something very new. So how do we measure EMF? So to measure EMF or PD, we use a voltmeter. We normally use a voltmeter. And a voltmeter is an instrument used for measuring electrical potential difference between 2 points. So it's a voltmeter. Most commonly, it is an analog voltmeter in most laboratories. Like this one is an analog voltmeter which has a pointer. An analog instrument always has a pointer, which moves across a scale in proportion to the voltage of the circuit. Sometimes we could use digital voltmeters. Some laboratories have such a digital voltmeter. It is digital, to just displays the value onto the screen. But what I'm just saying is that a voltmeter is the device we are going to use to measure voltage, especially if it is direct voltage. How do we connect a voltmeter in a given circuit? So because voltmeters measure PD between 2 points, because they measure PD between 2 points, and we said we can't talk about PD through, we talk about PD across, then the voltmeters are supposed to be connected between 2 points. So voltmeters measure the PD between 2 points in a circuit, and for this reason, they are connected across. We don't connect them through. We connect them across or in parallel between the points within any section where PD is to be measured. So what does that mean? If you connect them in parallel, it means you are going to join the positive terminal of the voltmeter to the positive terminal of the battery, and the negative terminal of the voltmeter to the negative terminal of the battery, but across. That will be in parallel. And since voltmeters are connected in parallel, we don't want to use them to cause a short circuit. We don't want to use them to cause a short circuit. In other words, we don't want current to flow through them because they are not intended to measure current. They are intended just to compare a difference between two potentials. And therefore, voltmeters should have a very high resistance to take as little current from the circuit as possible. Since we don't want current to go through the voltmeter because they are not intended to measure current, we should make their resistance to be as high as possible. And I think the highest number is infinity. Therefore, if the voltmeter is to be ideal, its resistance should be infinity. So the ideal resistance of a voltmeter is infinity. I'm explaining why we say it is ideal. Practically, we can't achieve infinity. We can't have an ideal resistance, but theoretically it would be infinity. That is, completely no current flows through the voltmeter. Of course, some small current flows through it, even when it is not intended to measure current. So, the voltmeter should have as much resistance as possible, yet the ammeter should have as small resistance as possible, simply because the voltmeter is intended to measure PD between 2 points, to compare potential between 2 points, yet the ammeter is intended to measure current through the circuit. That's why the voltmeter is connected in parallel with the device as shown in these diagrams, yet the ammeter is connected in series. So I want you to look at the connections here. That's what we mean by in parallel, that is across the device. Okay. So I'll just animate this to make people understand how we connect a voltmeter. So of course, in the absence of an analog voltmeter, we could have a multimeter. But if a multimeter is to measure voltage, it should be on the volt setting. So a multimeter on the volt setting. It should be on the volt setting because the multimeter will measure resistance, it will measure voltage, it will measure current, it may measure a lot of things. So if it is measuring current, it should be on the ampere setting. If it's measuring voltage or EMF or PD, it should be on the volt setting. If it's measuring resistance, it should be on the ohms setting. So you must tell the examiner exactly what this is, what you're talking about. So we must connect one end of the voltmeter on the other point, on the other end, and we also connect the other end to the other end. So this is what we call connecting across the device. So if you use a multimeter in the laboratory, I think that is quite something very easy. Sometimes we may not have a voltmeter or even a multimeter, but we have a galvanometer in the laboratory. Just like we saw with the ammeter, in the absence of a voltmeter, we could measure current using a galvanometer. But remember, a galvanometer, even though it has high resistance, the resistance might be not that big, but it would allow current to flow through it. Yet we want no current flow through our voltmeter. So we must make sure we make the galvanometer resistance to be as high enough as possible to prevent current from going through it, so that it doesn't register a current but instead compares potential between 2 points. So a galvanometer may also be converted into a voltmeter by the connection of a suitable resistor in series with the meter. Such a resistor is going to be called a multiplier. It multiplies. It has a multiplying effect. In other words, makes the resistance to be bigger. So how do we increase resistance? We have to have resistors in series. So the galvanometer is connected in series with a suitable resistor, which makes total resistance here to be large, so that if this is being used as a voltmeter, it doesn't register current, but instead it compares potential between 2 points. If the resistance is large, no current goes through, but it can compare the potential between 2 points. So the multiplier makes the total resistance high, so that the device is now only used to compare potential between 2 points and not to measure current. The multiplier is making the resistance to be high, so that it is not now used to measure or to register current, but to compare potential between 2 points, and therefore it will be acting as a voltmeter. One important thing to note is that in the absence of a voltmeter, a galvanometer, and an ammeter, we should be very careful to choose the most appropriate instruments. In many cases, we have what we call rapidly changing voltages, such as alternating voltages or alternating current. We saw that for an alternating current, we could use the AC ammeter. For alternating voltages, we can use the AC voltmeters. You can't use an analog voltmeter that we have already seen to measure current, which changes direction, or to measure voltage, which keeps changing direction. So we can use the AC voltmeter, or we can use the calibrated cathode ray oscilloscope. It should be calibrated. We shall understand what we mean by calibration of these underwaves. A calibrated cathode ray oscilloscope. We should know because an oscilloscope has a scale. So we should know what each of these represents, either on the vertical or on the horizontal, so that if a wave is generated on the CRO, we can know how to find the frequency, the period, and the voltage, and so on and so forth. So that is what we mean by being calibrated. So if voltage changes direction, or if we have alternating voltage or alternating current, we can use a calibrated cathode ray oscilloscope. A calibrated cathode ray oscilloscope. We shall see the oscilloscope under waves, or you might have seen it under waves, both in IGCSE and in AS Physics of year 12 of A level. So at your free time or in your laboratory, you can investigate potential difference. You need two cells, you need two bulbs, you need about 10 connecting wires. And I expect you to come up with or to set up your apparatus just like this. So connect the circuit and connect your circuit in this case, in this nature. And you should be able to know the difference between a series and the parallel. So you can measure the PD across the bulb if you have it alone and record the PD across the bulb. So you record your PD here and then repeat the experiment, this time having an identical bulb which is in series with the first bulb. If you have used a 6 volts battery, for example, if you measure the PD across each of these bulbs, if they are perfectly identical, you note that this would have, say, 3 volts and this is 3 volts. If initially you had 6 volts for one bulb, you might have measured the PD across one bulb to be 6 volts. But if you have two bulbs in series, you might have noticed that the PD across each of the bulbs is now 3 volts. What has happened? It's like when bulbs or when devices are connected in series, it's like they share the potential difference. But if you try to put an ammeter at any point in the circuit, you might have noticed that the ammeter gives the same reading. What does that imply? You will have investigated and observed that in a series, the current is the same, but the PD is divided. You must have observed this in your IGCSE, and you can just repeat this just to be very sure of what you are dealing with. So in series, the current is the same at all points. However, the PD is shared. The potential difference is shared. And I said if the devices or the components or the bulbs are identical, the 6 volts is shared equally. That is in series. The ammeter, if you put an ammeter anywhere in the circuit, you are going to notice that the reading of the ammeter is the same. Or if you put 2 ammeters or 3 ammeters at 3 different points along the circuit in a series, you must have noticed that the reading of the ammeter is the same. But if you put a voltmeter across each of these bulbs, you must have noticed that the PD across the voltmeter is going to be less than the EMF, but the sum of the PDs is going to be equal to the EMF, which means the EMF, the PD is shared, or the EMF is shared among the components. You can repeat this using these bulbs in parallel. So to connect them in parallel, this is what I expect from you. So assemble your circuit just like this. And let's say you are still supplying 6 volts. So put a voltmeter across any of the bulbs and notice what it gives. So you're going to notice that in parallel, If I put an ammeter anywhere, let's say this is an ammeter, ammeter. The ammeter here, called A1, will not read the same values as the ammeter A2 and A3. If these bulbs are identical, A2 and A3 may read the same value, but the sum of these may equal to the reading of ammeter A1. So it's like in series, in parallel, the current divides at the junction. We are going to see this under resistance again. So in parallel, the current divides. So the current comes at the junction and divides, and this is given by Kirchhoff's first law that we shall see later on. So in a parallel circuit, the current divides. But the PD, if I put a voltmeter across any of these 2 points or anywhere, it will give the same reading as the EMF. So in parallel, the EMF is the same as the PD across each of the components. So you should note that very carefully. At the junction, the current divides here, it recombines here. So the current divides at one junction, it recombines at the other junction, as given by Kirchhoff's first law. So the current divides, but the PD across each of the components in parallel is going to remain the same. That is a concept you mentioned in GCSE. So to sum up lesson 2, I want us to do a few self-check questions just for fun. If the current in a flood lamp is 5 amperes, what charge passes in 1 second? So just remember charge equals to I times T. In 1 second, that is 5 times 1, which is 5 coulombs. In 10 seconds, it will be 10. 5 times 10, which is equal to 50 coulombs. In 5 minutes, 5 minutes is equal to 5 times 60 seconds, which is 300 seconds. So 5 minutes is 300 seconds. So this is going to be current times 300, which is 1,500 coulombs. What is the current in a circuit if the charge passing each point is 10 coulombs in 2 seconds? So current is equal to the rate of flow of charge carriers. So we just divide 10 by 2, that is 5 amperes. 20 by 40, that is 0.2 amperes. 240 by 2 minutes is 2 times 60, which is 120 seconds. So 240 divided by 120, I think that is 2 amperes. Those are just for fun. They're very simple. Study this circuit in the figure, and why it is called 36.8. The switch S is open. There is a break in the circuit at this point. In which circuit would lamp Q and R light but not lamp P? So we don't want lamp P to light. So when the switch is open, we want Q and R to light. So when S is open, this is an open circuit, so none of them will light. This one here, we want to remember Q and R to light when S is open. So this one is correct because when S is open, there's a complete circuit complete circuit on the side of Q and R, so this one will light. P will not light. Then C, remember we want Q and R to light. So this will not light because first of all, there's an open circuit connection with the battery. So Q, there's no power supply because there's an open circuit connection with the battery. Then here, if the switch is open, there's an open circuit connection with the battery, it will not light. Then here, when S is open, there's an open circuit connection with the battery, so this will not light. So the question was, in which circuit would lamps Q and R light, but not lamp P? So the answer is going to be B. Okay. Using the circuit in the figure, which of the following statements is correct? When S1 and S2 are closed, lamps A and B are lit. S1 and S2 closed, lamps A and B are lit. This is not true. Why? The moment I close S2, I cause a short circuit, and we saw that when there is a short circuit, current will not flow through A. It will take this path. So it will only be B that would light if both S1 and S2 are closed. So A will not light. So A not light. Reason, there is a short what? Short circuit. So current will follow the switch will cause a short circuit, so current will follow through the switch without going through the lamp. Then S1 and S2, S1 is open and S2 closed. Of course, if S1 is open and S2 closed, there is no, it is an incomplete circuit. Incomplete. Or I can say open circuit. So there will be no current flowing because it is an open circuit. As long as S1 is open, there is none of them will light because it is an open circuit. S2 is closed. And I mean S2 is open and S1 is closed. So if S1, as long as S1 is closed, there's a power supply, there's a power in the circuit. If S2 is open, there's no short circuit, so both A and B would light. So the question is, using the circuit, which of the following statements is correct? With S2 open and S1 closed, A and B would light. So this is a correct statement. So for the first one, if both are closed, there's a short circuit. A will not light. It is only B that would light. When S1 is open, there's an open circuit. There's no current in the circuit. When S2 is open, the short circuit is prevented, but S1 is closed, there's a complete circuit, so current flows through both A and B. So the answer is C. If the lamps are both the same in the figure, and if ammeter A1 reads 0.5, so this one is reading 0.5 to that junction, what do ammeters A2, A3, A4, and A5 read? So of course, ammeter A2 is going to read the same as ammeter A3 because they're in series. And ammeter A4 is going to read as the same as ammeter A5. But they say the lamps are the same, so they are identical. So we expect that the current divides equally. So this should take 0.25. The other one should also take 0.25. So each of them is going to read 0.25 amperes, 0.25 amperes. Okay, that is in accordance to Kirchhoff's first law. The sum of current into the junction is the same as the total current leaving the junction. We shall see that later on. I think this should be the last for today. See you in lesson 3.